you for the introduction and also for the invitation to this wonderful place, to this conference. And I would like to, hopefully I try to be minimally technical. This is the last talk. This is a late hour, and I'm more or less what separates between you and the drink. So I'll try to be as least technical as possible, and we'll show you some nice pictures. So basically, I would like to show you a few snapshots of a line of work that I did with this list of colleagues of mine from different places. Basically, the main motive of these works was the study of deformable three-dimensional geometry. Basically, we started with adventuring with computing deformable correspondences, and then I always dreamt about doing synthesis. So I will show you some results with shape synthesis. And the common denominator, or maybe the main take-home message that I would like to try conveying is that basically, if you can model something as opposed to learning it from the data, try modeling as much as you can. Then you will need to learn less. You will have less degrees of freedom to learn. You can use less data. And basically, it will work better. So I will show you some examples to support this statement. So I already showed this slide in the opening of the conference. So basically, I think nowadays the technology driving the 3D acquisition market has made a huge leap in reducing the size, the power, and increasing the quality of depth sensors. They are now our intimate companions. Basically, Apple is already producing smartphones with a 3D sensor. So basically, there is a deluge of 3D data, of user-generated 3D data that we find around us. And of course, we can argue, we already argued about this in the beginning of the conference, whether in the long run you really need 3D sensing or not. But I would say that 3D sensing is here to stay for many years, maybe before we find something else. And of course, an important question to ask ourselves is basically what to do with these data, how to analyze them, how to process them, what to do with these data. So we'll show you some examples of works that other people did. So this is, for example,
her name's Mandy.
A technology developed by the company FaceShift.
6'4", good with an axe, and likes the music of Lana Del Rey. Socially sexy, and when necessary, extremely violent.
So basically, as you can see here, a 3D camera, in this case an Intel RealSense camera, is used to scan a 3D video of a human actor, and then transfer the motion, the expression of the face to an animated character. And this is done without motion capture markers. This is, of course, a significant simplification of the acquisition procedure for the motion picture industry. Of course, there are many other applications, like in robotics, in augmented reality, in virtual reality. And basically, there are a few basic ingredients underlying these problems. So one of these ingredients that I would like to dedicate most of the time to is the problem of finding correspondences between shapes. So for example, if I have two human shapes, I would like to take a point on this shape and tell which point on the other shape corresponds to it. And somehow our brain knows how to do it very well. At least apparently, we think that we know how to do it very well. It's a problem that, in this case, can be formulated very rigorously in geometric terms, because these are just two different poses of the same object. We know that articulations of our bodies are approximately isometric, so there is a geometric quantity that is preserved under this transformation, and we can find a map that minimally distorts, for example, some intrinsic distance, geodesic distance, or some other intrinsic quantity. If we go to another shape still belonging to this class of human shapes, but having a different geometry, well, the previous statement is maybe not a correct one. We probably need something else, some other invariant, something that is probably much harder to model geometrically, but probably can be learned from data. So we have some framework, some axiomatic framework that we can start with, but then we need to probably do learning. And of course, in real life, we have lots of other complications. Like, for example, most of the cameras that you will find today will scan just what the light, what the camera sees. So what you have behind is invisible. It's occluded, or you can really perfectly segment the object, for example, from the floor on which it is standing. So then you have some clutter as well. And noise, of course, acquisition noise due to motion, due to low signal, and so on. Basically, we need to cope with those challenges as well. So I would like to show some ideas how to use geometric structures and use learning that incorporates these geometric structures for solving deformable correspondence problems. And then once you know how to solve deformable correspondence problems, I will show you that it will be useful for solving synthesis problems. So this is a very simple synthesis problem. Actually, it's a very powerful work, Kinect fusion, and basically there are a few continuation works that followed it. Basically, if you take a few frames by using the Kinect sensor, it will more or less look like this. There will be a lot of holes because the picture is occluded, and you would like to reconstruct a full model. So basically, you either ask the object to rotate, or you rotate the sensor, and you would like to fuse those views into a single model. So you synthesize a new model. And the main challenge here, of course, is when the model deforms as you're scanning it. For example, the human continues to walk or to change the pose, and basically the problem is not even well defined. So I will show you some ideas that could be useful to solve this problem. So here, Kinect fusion relies very much on doing tracking. You need basically a very dense 3D video to do this reconstruction, because then you can assume that there is a very small incremental deformation between one frame and the following frame. What I will show you is that you can do it with very distant frames, with very distinctly looking frames, but you will need the correspondence, basically a full correspondence to be solved between the frames. Okay, so let's start with the correspondence problem, and basically in its simplest formulation, correspondence problems, I'm going to model shapes as two-dimensional non-Euclidean manifolds embedded in the three-dimensional Euclidean space. So I have the surface embedded in R3, and a correspondence will be a pointwise map, a function that maps a point on X to a point on Y. And if you try working with these objects, it will be a little nightmare, because it's not even obvious how to parameterize them, how to do optimization on these class of objects. There is usually no global system of coordinates on a manifold. And when you encounter such situations, a very common trick in engineering is to do what is called lifting. So basically, you have a complicated object operating on something, this is basically a map between manifolds. So try increasing the complexity of this space, but in exchange, get something easier for the map itself. And this idea has been there forever, but basically, probably it's due to the works by Max Ovsyannikov and other people from the Stanford group that actually elaborated the details and evangelized this approach. So basically, the idea is that instead of thinking of a map between points, think of maps between functions. So you have a real valued function on the manifold X, and you take an operator that takes a function in and spits another function on the other manifold Y. Okay, so now you have a map between functions. And it's very easy to show that this map has to be linear, just because of the properties of composition of functions. So you have a much more complicated space of real valued functions on manifolds. However, the object itself that you are interested in, the map itself, is a linear map. It's a linear function. It's a much more tractable object. Okay? So what I'm going to do next, I'm going to equip our manifolds with a basis and represent this linear map in a basis. Okay? So basically, one of the common bases that is used on manifolds is basically the generalization of the Fourier basis to non-Euclidean spaces. So what I'm showing here is a reproduction of a very famous experiment that the German physicist Ernst Chladni did about 150 years ago. Basically, a metal plate covered with sand, connected in this case to a loudspeaker, and you see patterns forming, corresponding to different frequencies. So basically, the vibrations of this plate are governed by the wave equation, and for some set of frequencies, the wave equation will have a separable solution. The spatial part and the temporal part will split into a product of two functions. And basically, the spatial part will be governed by what is called the Helmholtz equation. Basically, this is the stationary part of the wave equation, and mathematically, this is just the eigendecomposition of the Laplacian, or the non-Euclidean equivalent that is called the Laplace-Beltrami operator. And basically, its eigenfunctions, the solutions of these equations, are called the vibration modes of the plate. What you see here are the zero crossings of these functions, where basically the plate never oscillates, and the sand doesn't move and remains in these patterns. So basically, the space of functions is an orthogonal basis. It's equivalent to the Fourier basis, and we can equip our shapes with these basis functions. So now, if we have a function f on this cat shape, we can decompose it into a Fourier series, or maybe truncate the series after some k number of frequencies, and basically we have an approximate decomposition of the function into a Fourier series with coefficients ai and basis functions phi I. We can do the same for the corresponding function g with respect to the other basis, psi I with coefficients bi. And basically, we have a linear operator relating between f and g. So we can write this linear operator with respect to this pair of bases as some k by k matrix C. Okay? So basically, our correspondence, this complicated object, correspondence between two manifolds, is now captured by a k by k matrix. So if I now am given two sets of Fourier coefficients, basically, the correspondence will translate one coefficient in one basis to another set of coefficients in another basis. And if I'm now given a set of knowingly corresponding functions, let's call them probe functions, so I have a function fi on x, a corresponding function gi on y, I just solve a linear system of equations and I have the correspondence. Okay? So basically, the problem is reduced to a much simpler algebraic problem. Now, of course, the question is where to take these probe functions. And this is a standard problem in computer vision, of course. Basically, the computer vision approach to find these probe functions is to build descriptors. So imagine that I have some black box, some black magic, that takes a shape and attaches to every point on the shape a k-dimensional vector. Let's call it a descriptor. Okay? So if this black box knows to produce such descriptors in a way that is sufficiently repeatable under a certain class of deformations, I will have the same probe functions repeatedly, right? So if I now take an ith coordinate in this vector-valued function and think of it as a scalar-valued field on my shape, basically I have the ith probe function. And if my descriptor is good enough, then on some deformed version of the shape, I will have the same function. I don't know how the vertices are numbered or how the vertices are sampled, but this is exactly why I'm solving for the linear system of equations, right? To find this correspondence. So basically, the question is how to find this probe function. And there is a wealth of literature showing how to construct axiomatically such functions, for example, studying the propagation of heat or the behavior of waves in non-Euclidean domains. But basically, all these approaches can be useful for real data to some extent. So there are some properties that you would probably like to keep, like you would like to be intrinsic, insensitive to isometries. You might want to be scale invariant, and basically this can be built by construction. But real data will exhibit some more complicated types of invariance that you would like to capture, and here you must resort to learning if you want to make this leap in performance of the correspondence. So basically, you would like to learn these descriptors. So let's do the following simple experiment. We'll take a very standard approach to descriptor learning. So descriptor learning can be viewed as metric learning. So you will see immediately why I'm mixing these two problems together. So imagine I'm taking a neural network, or whatever your preferred way of doing nonlinear maps, parametric linear, nonlinear maps. I'm going to put some raw descriptor into this machine, parameterized with some parameter theta, and I will spit out some new descriptor. Okay? So I created a new descriptor space. So imagine now I have a couple of such nonlinear maps parameterized with the same parameter, so I'm coupling them together like two Siamese twins, and I'm putting inside two shapes with basically two points that I know that should correspond. I know because I have some ground truth, a human observer label, that these are two corresponding points. And I would like, of course, the corresponding points that are produced in the new descriptor space to be mapped as close as possible to each other. And if I have two negative pairs, basically, if I have, sorry, two negative points, a negative pair that I know that should not correspond, I would like the points in the new descriptor space to stay far away from each other by some margin. Okay? So basically, I can translate this into a loss function that incorporates a loss on the positive pairs. I would like this distance to be minimized, and some, let's say, hinge loss with some margin mu that I would like to be, this distance to be maximized, or basically, I would like the margin to be kept between negative pairs, between descriptors that are not corresponding. This is a very standard way of learning descriptors. Essentially, we are learning a distance function on a new space into which we are embedding the descriptor. So that's why it's a metric learning problem. And here, this distance function is just the L2 distance. And basically, all the complexity of the map is this parametric map, this neural network itself. Now, if we apply this idea to our problem, let's say we look at the CMC curve. So we order the matches by their distance in the descriptor space, and we compare this to the ground truth correspondence, the hit rate, how many matches we had within the first k best matches. Of course, this technique will outperform the raw descriptor quite significantly. And here I'm just using what is called the shot descriptor, which is a local histogram of normal orientations, which is not intrinsic, but it is local, so it is very insensitive to even to significant bending transformations. However, this learning approach doesn't take into consideration any geometry of the problem at all. It doesn't take into account that I'm going to use these descriptors, for example, to solve for correspondences using this functional representation. If I use a more geometrically meaningful criterion, for example, I take a certain radius around the ground truth correspondence point, and I ask whether or how many points fall within these, basically how many correct matches I'm getting within this tolerance radius, you will see that basically there is practically no improvement between the raw descriptor and the learned descriptor. Because again, the learning didn't take any geometry of the problem, any structure of the problem into account. Okay? So basically what you could do instead, you can actually take into account that these descriptors are going to be used, first of all, they are going to be projected onto our Fourier basis. Then we are going to solve a least squares problem. And then using this least squares problem, we are going to recover a pointwise correspondence. And that will be the basis of our loss. So if we modify our training scheme in the following way, we again learn a new set of descriptors. We project them onto the Fourier basis on shape X, shape Y. We get the corresponding Fourier coefficients A and B. Then we solve for this functional map, basically for this matrix C. This is the least squares solution to the linear system of equations, matching between the Fourier coefficients A and B. What we are getting as the result, so basically if I now project this matrix C back onto the pair of bases, I synthesize my correspondence back in the space domain, in the standard basis. Because I did truncation, it will not be perfect. It will be sort of a band-limited approximation of the correspondence. It will be blurred. For example, if I take this point, this green point on the source shape, the corresponding, basically the corresponding matrix that I will get here will look like this. It will be sort of a blurred delta function, right? Because I threw the high frequencies by doing this truncation. So I can take the absolute value and normalize it to sum to 1 and interpret this as a probability distribution function. So basically, it's the probability of a point here being in correspondence with a point here. Okay? So with respect to this probability distribution, I can compute moments. For example, I can take the geodesic distance squared, for example, between a point on Y, on the shape Y, and some ground truth correspondence of a point X. and compute this second-order moment. It will have two terms, of course, some bias and some variance. The variance comes from the fact that we did truncation. This is exactly this blur that we had. And we cannot control it except by increasing the number of basis functions. However, the bias itself can be minimized by learning, right? And this is the target of our learning. Basically, we would like the bias to be 0, and then by finding the mode of this distribution, by finding its peak, we are going to recover correspondence. Okay? So if you do this trick, if you do this kind of learning, it doesn't improve in terms of the CMC curve, but if you look at the geometrically meaningful criterion for evaluating the correspondent, it improves a lot. Basically, because now the learning is aware of how the descriptors are going to be used. You incorporated the geometry of this problem into the learning problem. And it's a very simple modification. Basically, this least square solution is perfectly differentiable, so you can use it with standard learning tools. We used TensorFlow in this case. And basically, you have a significant improvement in performance. So I will show you some more experimental results with this learning idea. So now let's go back to our functional correspondences. Sorry. Let's go back to our functional correspondences. And remember that this was a very convenient way to represent correspondence, because if we want, for example, to chain a few maps between different shapes, we just multiply matrices. But eventually, in many applications, at some point, you would like to get a pointwise map. Okay, so you need to convert that functional representation of the correspondence into a pointwise map. And there are many standard ways to do it. Basically, the literature is full with different algorithms. The problem is that most of them, or all of them, practically all of them, they don't guarantee a smooth map or even a continuous map. So for example, here you can see indicated by these green points are points that have no pre-image under the correspondence. So basically nothing maps to them. It means that the map is not surjective. And of course, if you do, for example, if you use this correspondence for texture mapping or for some other high-quality computer graphics manipulation, this is a disaster. You cannot use it, right? Because basically you want the map to be surjective, and probably not only surjective, but smooth. And there is no place in the original framework where this smoothness or surjectivity or bijectivity is enforced or imposed. So let me show you another geometric structure, another way of viewing correspondence from the geometric perspective that will guarantee the recovery of a bijective correspondence. So again, I need a four-dimensional display to show you these visualizations for two-dimensional shapes, and the conference didn't provide me with a four-dimensional display. So let me show you two-dimensional shapes, basically, or one-dimensional shapes, basically contours. Of course, correspondence between contours is a boring problem. It's a solved problem in many senses. But basically, this is just a visualization. Of course, we are going to use the same. This is just a metaphor to going to two-dimensional and higher-dimensional objects. So basically, if I now consider the product of these two shapes, each shape is homeomorphic to a one-dimensional sphere, to a circle, right? The product of these two spheres will be a torus, right? This is the product space. So one coordinate is the location on shape X, another coordinate is the location on the shape Y. And if I now find correspondence between these two shapes, I can think of it as a one-dimensional manifold, as a path in the product space, okay? So I don't want to draw it on a torus, so let me draw it just on a parameterization of the torus on the unit square, and remember just that we have cyclic boundary conditions on the left and the right, and on the top and the bottom, okay? So here is an example of a correspondence. I'm parameterizing the two shapes in such a way that this identity map is the perfect correspondence, and then I take 2 points, xi and xj, and I swap the correspondence. And these are basically these two holes on the diagonal, okay? So basically, I'm given a noisy correspondence. So now think of this correspondence as an image drawn on this non-Euclidean product manifold. And I would like to denoise this image. Basically, I would like to do some kind of enhancement, some kind of denoising, some kind of inpainting, some kind of super resolution, if you will. Basically, all these metaphors from image processing could apply here. You just need to take the metric of this non-Euclidean space into account, but basically everything else will work the same. So now I would like to do inference of the good correspondence using this noisy input. Okay? So let's do the following thing. I will do diffusion on X. I will do blur on X. So basically, this will correspond to blur in the horizontal direction in this product space. Okay? Then I will do blur on Y, which will correspond to blur in the vertical direction in this product space. And now let's find the best bijective correspondence that maximizes the amount of black in this picture. Okay? And this will be the result. You see, we canceled out the noise. Okay? Of course, in practice, you would like to do it on some four-dimensional non-Euclidean product space, and your bijection is a two-dimensional manifold. Okay? So it's a surface, it's bumpy because it's noisy, and you would like to straighten it. Think of some piece of rubber that you would like to iron. Okay? And actually, this analogy of rubber is helpful. I will show why it is helpful in a second. So another one-dimensional illustration, we have an interval. Let's say I take two peaks on these, two deltas on this interval, one centered at 0.8, another one centered at 0.20. I diffuse them on this interval. This is shape X. So I get two bell-shaped distributions. Of course, the modes are still at 8 and then 20. Okay? Then I map them to the target space Y, and my correspondence is noisy. So every point is mapped perfectly according to the ground truth correspondence, except 0.8 and 0.16, which are swapped, as in the previous example. Okay? So as a result, you get this. Now you do diffusion on Y. So diffusion will remove these spikes, and you will get this. You have larger distributions still, but their modes are exactly at 8 and 20, okay, where you expect them to be. So, so this is sort of a visual explanation why this works. Okay. So basically, what we have is a kind of a filter in the in the product space. We call it a product manifold filter. You take some input correspondence. You can think of it as a permutation matrix, but it doesn't need to be a permutation matrix. It can be sparse. So some columns and rows could be zeros. It can be a distribution. It doesn't necessarily have zeros and ones. It can be noisy, of course, and then you do diffusion on X by multiplying it by this diffusion kernel. Think of a heat kernel in a manifold on the right. Diffusion on Y, diffusion kernel on the left. You basically operate on the rows and the columns. And then you would like to get a bijection. So basically, you want to project it into the space of permutation. So basically, you maximize the inner product between a permutation pi and this diffused version. And this is a linear assignment problem. Okay? So it can be solved efficiently in polynomial time. And you iterate this process. You can iterate this process. So just an example with a sparse correspondence given as the input. So you have 20 a set of 20 points with very accurate correspondence. So I'm showing here, this is the input. So most of the points have no pre-image under this map. Therefore, it's all green. And this is the geodesic error to the ground truth. Of course, at those points that you can see here, the error is very small, but the error is very big. It's like basically Voronoi cells on the shape. You do a few iterations of this product manifold filter, and the result is actually much better. So you can see how the texture maps well from the source shape, from this source shape to these target shapes. Basically, you can see that you get a very high frequency, basically accurate correspondence up to high frequencies, and this is visualized by basically by the fact that the texture is mapped very well. Okay, and basically these errors that you started with are blurred by the iterations. So if you take, for example, if you use functional maps and take two standard algorithms that probably are the best in the literature nowadays, you use either the iterative closest point algorithm that most of the people use, or the coherent point drift, which is a smarter way of recovering pointwise correspondence from a functional map. You get these non-surjective maps. You just apply a single iteration of the product manifold filter to this result, and you get much lower error, much nicer looking correspondence, which is guaranteed to be a bijection. Okay? So again, this is just the same evaluation that we had before, tolerance radius on the horizontal axis, the number of correctly found correspondence within that tolerance on the vertical axis. This is the result of 3 different ways to recover pointwise correspondence from a functional map, and this is the result of their filtering using the product manifold filter. Okay? This is the result on real scanned human shapes from the Faust benchmark. The combination of the learned descriptors with the product manifold filter is here. And basically, other curves are other existing methods. So basically, it's a very naive experiment, because in the way we learn the descriptors, we never took into account this post-processing by the product manifold filter. Still, it works quite well. So I will show you that this manifold filter actually minimizes the quadratic loss. So this quadratic loss can be incorporated at learning stage, and if you do it, it works better. The only problem is that the Faust benchmark becomes too simple to test this improvement, because basically very few cases are basically the correspondence is almost perfect, right? So you need a better benchmark. So I will show you a few alternative interpretations to this procedure. So one of the interpretations is the following. So basically what we have is this iterative procedure. We first do diffusion on X, diffusion on Y, then we solve a linear assignment problem. Basically we minimize this linear objective. This pi k is fixed. This pi is the optimization variable. We solve this linear, we maximize this linear objective on a simplex, right? Basically the convex hull of the permutations. Basically, there is a simple equivalence between maximizing this objective on the discrete set of permutations and on its convex hull, because of the total unimodularity property of this space. Basically, you can solve it using linear programming. And so basically, it looks suspiciously familiar. Basically, you are solving a sequence of linearized problems, right? Basically, there are many names under which this can go. Or you can, for example, see in it the Frank-Wolf algorithms, or convex concave procedure, or conditional gradient descent. Basically, all these names refer to the same idea. Basically, you have a quadratic objective that you are sequentially linearizing, and the linearized version is a linear assignment problem. So this is a quadratic assignment problem. It's an unsolvable problem. It's an NP-hard problem. But basically, you do a sequential linearization, you find a local solution to this problem. And surprisingly, it works very well. It works efficiently. Basically, another way to write this maximization problem is write it as a minimization of this kernel mismatch. So you have 2 sets of kernels on X and on Y. Kernels encode pairwise relations between points. Think of them as a proxy to distances, diffusion distances in case of heat kernels. So you have 2 distance matrices or 2 kernel matrices, and you would like to permute the rows of one and the columns of another, or actually, basically permutation is an orthogonal transformation. You can put this pi with a transpose here. So basically, you want to permute the kernels in such a way that they will disagree minimally between each other. So basically, you are involving second-order relations, basically pairwise relations between points in the correspondence problem, something that was missing in the original formulation. And it seems to be a strong prior. I will show you a few other interpretations of this problem, and then I'll show you some surprising results. Another relation is to minimization of bending energy, or Dirichlet energy in the product space. So let's take the Dirichlet energy on X. So Dirichlet energy, think of some function as a rubber shell that is not at rest, right? Basically, if it is flat, it has no curvature, then it will have 0 bending energy. Once it has some curvature, it has non-zero bending energy. It's basically the potential energy of a spring, essentially. And the Dirichlet energy, this term, exactly encodes the amount of energy that this elastic shell has. So basically, by minimizing this quadratic form with the Laplacian, we are minimizing the Dirichlet energy. It can be equivalently seen as maximizing this quadratic form with a negative exponential of the Laplacian, which is nothing but the heat kernel with some time constant t. Okay, so basically we are maximizing this quadratic form with the heat kernel. Now look at what we had in our case. We were maximizing this quadratic expression. If you think of this matrix pi, our permutation, if you parse it into a long vector, what we have is this quadratic form with this tensor product of kx and ky, which is nothing but a heat kernel on the product space. So basically what you have here is a Dirichlet energy that is being minimized by our procedure on the product space. Of course, it has some non-Euclidean geometry, but you start with a correspondence that looks like a very bumpy, very high energy shell, and you try to straighten it. You try to make it as smooth, as flat as possible. And this is basically what this minimization procedure does. Another interpretation, you can think of it as an iterated blurring and sharpening. So essentially, if you take this product of the two kernels with the input correspondence, and now let's decompose, let's represent the kernels in their corresponding Fourier bases like this. Okay, so it's just, basically the heat kernel is just a non-Euclidean generalization of the Gaussian, right? And this T controls the variance, the bandwidth of the kernel. Now, if you take this expression is nothing but a functional representation of our permutation, of our map. Okay? This matrix C. So what we have is a low-pass filter. This is basically a Gaussian low-pass filter, or it's non-Euclidean analogy that we are applying to our input correspondence. We are smoothing it. We are doing low-pass filtering. And then we are building the correspondence back in the space domain. And of course, then we do conversion to the pointwise map. So essentially, of course, every single signal processing person will know that if we do this smooth windowing, Gaussian filtering in frequency corresponds to Gaussian frequency in the space domain. It's a very smooth window. It's probably the smoothest window that you can imagine. And it eliminates the Gibbs phenomenon, or it attenuates the oscillations that you would otherwise have if you did a rectangular window, basically, by just cutting off portions of the signal. And basically, this iterated smoothing and sharpening is the projection on the space of permutations. It reintroduces high frequencies. Basically, this sequence of operations is essentially what the product manifold filter does. And you can think of it as a sequence of linear operations followed by a projection. And this is what a feed-forward neural network does as well, right? Basically, you think of several iterations of this filter, let's say up to iteration k. You have a sequence of linear operations and projections, linear operations and projections. It would be actually very interesting to see if you can replace this projection that currently requires an iterative algorithm, basically a linear assignment problem solver, by something smarter, something that takes less computations. Okay, and basically learn the rest. This is something that we are currently trying to do, and apparently it works more or less like the original version at a fraction of the computational cost. I will show you a few examples. Here, the correspondence is initialized with 2 points. This is the result. Here, similar colors represent basically where the points are mapped. Okay, so just 2 points as the input, no additional assumption. The correspondence looks perfect. I can show you an example with 1 point as well. Here's an extreme example. Basically, there is no continuous map between this one-dimensional shape and this two-dimensional shape. No such a thing exists. And as you can see that the outcome, of course, is discontinuous, but somehow the discontinuity, first of all, the correspondence makes sense if any correspondence here can make sense. And the discontinuity somehow is minimized. I will show you another example. So there is no continuous map between a sphere and a torus. So I start with a random initialization. Actually, we did this experiment for many hundreds of random initializations. And this is the outcome. It always looks like this. So there might be some rotation along the big circumference of the torus, but this discontinuity always lies inside. So it's somehow as if we were minimizing the length of this discontinuity. So of course, this somehow leads me to think that this procedure can be used to find canonical parameterizations for shapes. There is no canonical way to parameterize a two-dimensional domain or anything that is of higher dimension than 1 because of lack of total order relation between points. But this is probably the closest you can get to a canonical parameterization. Okay, one important thing that I didn't mention yet, basically how we choose the kernel. And currently this is a completely arbitrary trial and error procedure. So if you take a kernel with a large variance, so this is again an example between contours, you initialize randomly. So this is the result of the first iteration, and after a few iterations, we converge to a ground truth correspondence from a random initialization. If you take a smaller variance, then you might get stuck to a local minimum like this, and the correspondence will look discontinuous and unnice. Still a bijection, but not a useful one. So we currently just do more or less a trial and error choice of the kernel. Of course, a much better way would be to learn the kernel from the data, the same way we did for descriptors. Basically, putting this into an end-to-end learning scheme is something that we are working on. So basically, I guess I will briefly summarize this, and then I would like to show you some results with shape synthesis. So basically, I guess my main message was that it is useful to incorporate, first of all, to understand the geometry of your problem and incorporate it into your learning if you need to do learning at all. It reduces the number of degrees of freedom. It, as a consequence, allows you to use less training data. So in our case, we had a tiny neural network. So I don't remember now how many parameters, but tiny compared to what computer vision people use. We had a very small training set. I think something like 20 or 30 subjects, maybe about 10 different poses of each subject. So really a tiny data set compared to, I don't know, to ImageNet, for example. But still it produces very good results, actually state-of-the-art results for this category of problems. Another geometric idea was to regard correspondence computation as sort of denoising of an input correspondence, of a noisy input correspondence in the product space. And here probably you can do much smarter things. We use just two diffusion kernels. You can think of them as a separable kernel in the product space. You can do much smarter things, some analogy of, some non-Euclidean analogy of bilateral filter or non-local means, or you can, of course, do learning of these kernels. Basically, I think all the analogies to impeding, to denoising are pretty endless here. It works surprisingly well and fast. So basically, it's a quadratic assignment problem that we are solving, but we can solve it for many tens of thousands and hundreds of thousands of vertices in several minutes. So it's pretty fast, considering that if you try to solve it basically just as a combinatorial problem, NP-hard problem, it's unsolvable maybe for 10 vertices already. We have interesting interpretations. I've showed some of them. We have many more that you can look up in the papers. We have code available, so if you need to find correspondences in your problems, I really welcome you to try our code, and I will be happy to assist you with it. But basically, one of the applications that good correspondence enables, and I showed you just the setting of full correspondence. Of course, it can be generalized, it should be, and it can be generalized to the partial setting. I don't have time to show it, but basically in the partial setting, we can discard some of the points that have no correspondence on the target shape and the other way around. Once we have good partial correspondence, we can solve synthesis problems. And I would like to show you some very recent result that we had with synthesis problems. So basically, I would like a magic box that knows how to generate human shapes. Okay, so I push a button, and I would like a human shape to be spat out. Now, there are two categories of approaches that exist today to this problem. So one approach is what computer graphics people are frequently using. So you work really hard, you read your human model, you attach a skeleton to it, and then you move the bones of the skeleton. So then you have perfectly looking shapes of the human body. If I now want to create a dog, go again, rig the dog model, do this manual work of fitting the skeleton, and then you have a model for dogs. Another approach is a completely data-driven approach. So basically, people usually rasterize the shape into a volumetric image, and then you use volumetric three-dimensional CNNs with tens or hundreds of millions of parameters, tons of training data, and it works. So it learns all the invariances that pertain to this class of shapes, learns the class of shape itself. It can generate human figures. But basically, it's hugely wasteful because you know a lot about the geometry of your shape. So basically, what we tried instead was to use a variational autoencoder in exactly the standard setup that variational autoencoders are used for synthesizing images. But now we perform convolutions on the mesh. And there are many ways to construct some analogy of convolutional neural networks on a mesh. We used the approach proposed by Edmond Bouillère and his students from 2017. Basically, it's a kind of a graph convolutional neural network. In our case, the graph is the mesh. So first, we build a variational autoencoder in the following way. We take a collection of shapes, in our case, human shapes. We don't make any assumption that this is human. It can be any shape. I will show you faces as well. Basically, we take human shapes, we pass them through this convolutional neural network, map them into a bottleneck, basically, which is the representation space, the latent space, low dimensional, in our case, 128 dimensional latent space. Then we pass them through a decoder, a deconvolutional neural network that produces embedding coordinates for the mesh vertices again. So of course, the only real assumption that we need about this collection of training shapes is correspondence either between them or to some reference shape. Okay? So basically, we want their vertices to be indexed in a consistent way. Okay? So basically, we learn this encoding and decoding process. Once we train the autoencoder, we throw the encoder. And we have basically a map, a highly nonlinear map from the latent space. I place a point in the latent space. I get a human shape out. Okay? Now, once I have this way of representing human shapes, now I'm given an input. Let's say this very partial point cloud of a human body. So I will find its correspondence to the reference shape. And now I ask myself, what is the point in the latent space that lies the closest to this input? Because I already established the correspondence, I don't need to do any matching anymore. Basically, the points are already in correspondence. I can just minimize, let's say, an L2 distance criterion. And I do optimization on the latent space. Of course, it's a highly non-convex optimization, but it converges into something like this. So I will show you some examples. First of all, random sampling from the latent space. So basically, magic box, here a random input, give me a shape. And you can see that, well, these are not perfectly looking human shapes, but they're kind of human, right? So probably we can do better. So as always with VAEs, with variational autoencoders, there is a trade-off between how Gaussian is this distribution and how well you represent the inputs. This is kind of a trade-off. But this is still unconditioned by any input. Still looks human, not perfect, but human. Now, let's explore a little bit the configuration of this latent space. So I will do the following. I will encode this shape, and I will encode this shape into 2 points in the latent space, and I will do linear interpolation. Of course, every point on this line segment will correspond to a human shape, right? So I'm outputting a few. So you see that I'm interpolating both the identity and the pose. And I'm interpolating it in a very naturally looking way, right? If you just do linear interpolation in the original space, horrible results will basically horrible deformations will happen that depend on the pose. We are not explicitly separating between identity and pose. Of course, this is something that can be done of course we will do it. Another example, again, interpolation in the latent space. More interesting algebraic manipulations that you can imagine. So suppose I have this shape Z with the right knee raised. And then I have 2 shapes with the same subject with the left knee raised and left knee lowered. So if I take the difference, it tells me lower the left knee, right? This is what the difference tells me, this vector, this direction. If I take this combination of the right knee raised plus this direction lower the left knee, surprisingly, the right knee will go down, as you can see here. And we never explicitly taught the network to, that there exists this symmetry between left and right in the human body. So this is somehow that was somehow emerged by itself from the training process, which is nice. A few examples of shape completion. So this is a Kinect depth image, a point cloud, the corresponding completed shape. Another example, a few scans from the Faust data set and their completed version. It's not perfect, but at least it's a watertight, nice mesh that corresponds to the input. Now, because we are initializing our optimization problem with a random point, if we have some lack of constraints, for example, here we have no arms, so there is no constraint on the arms. Every time we initialize randomly, a different configuration of the arms will come out. So here are a few different completions of this shape. There is no one way to complete this shape, so it's nice that you can explore different possibilities. Here we have even less constraints, so these are the possible solutions. Now, this is a hack, but it works to some extent. I can complete each of these shapes, so each completion will correspond to some optimal point in the latent space, and then I can find the centroid, in this case of these three completions. I will get basically a fused shape, fused from three viewpoints that have completely different poses. So basically, I will produce some interpolated pose. It will be none of these poses that I observed in my input. But basically, I guess the problem of choosing the pose in this case is not well defined. So this could be a plausible solution. Just a few examples, and I will finish. Just a few examples with faces. Again, shape completion with faces. You can see that here major, basically, portions of the face are missing. Wherever you have the input, it constrains the reconstructed shape. And well, it's not the highest resolution shape face model that you can imagine, but still it produces something that looks like a human face. Okay, so I will stop here. I know that I ran out of time, and will be happy to answer your questions. Thank you very much.